Serial wire viewer is ready and we can start actual coding. And to do that, first let's look at this illustration. Okay, so we have a microcontroller, we have the sensor, and to communicate with the sensor we need to use SPI interface. SPI stands for Serial Peripheral Interface. If you're not aware what it is at all, think of it as the USB. Okay, so we have a mouse and we have a USB, so we can send data to a computer through USB protocol. So SPI is pretty similar to that, but compared to USB, it has very simple protocol. Okay, so you don't need to have extensive knowledge to understand how the SPI operates. In addition, we will use HAL API that will handle all the complexities, so we just need to use some functions. However, I decided to prepare a few slides about SPI interface so you have general idea how it works, and it will help us to configure SPI interface easily. And first, let's look at the pinout of the SPI interface. So in the SPI interface, we have a master, which is a microcontroller usually, and we might have several slaves or several sensors connected to the same SPI interface. And here we have this wire serial clock, which is to synchronize data. Then we have a master in slave out MISO line. So through this wire, a slave can send data to the master. Then we have MOSI, master out slave in. Through this line, a master sends data to a slave. In addition, in SPI interface, the master cannot communicate with several sensors, several slaves at the same time. So it is not parallel communication. Therefore, we have these chip select lines to choose the slave to communicate with. For example, if master decides to communicate with this slave, it will keep the corresponding line low, logical low, or let's say 0 volts. And at the same time, it will keep other chip select lines high. So this slave will listen a master, so it will wait, it will expect some data from the master, and other slaves will be in reset station, so they kind of shut down. So through these chip select lines, we can choose the slave to communicate with. Next, let's look at this diagram from the datasheet. So it's a block diagram of the ICM20948 sensor. And here we have sensors, X, Y, Z acceleration, and accelerometer and the gyroscope. And the output of the sensors is, of course, analog signal, okay? So it's kind of some signal it is recording. Then we have ADC, analog to digital converter. So it will convert this analog signal to a series of numbers. So for example, 53, 45, and so on. And all this data that represents this sensor analog data will be stored inside of the sensor registers. Okay. Sensor registers. The IMU sensor or any other sensor contains usually multiple registers, and the size of each register is 1 byte, or in other words, 8 bits. Okay. So you can think of the sensor memory as a table, okay? So we have many registers. Okay, so every row, let's say it's a 1 register. And in every register has its own unique address. So this register might be register 0, this might be 1, this might be 2, and so on. And we can write to certain registers, and it allows us to control how the sensor operates. For example, register 1 might be responsible for the sampling rate, how frequently the sensor will sample data. In addition, we can read registers to extract information from the sensor. Okay, so for example, there might be register 3 that holds acceleration data along x-axis. So by reading this register, we can extract x-axis acceleration. So all the data will be stored, will be mapped inside of the registers. So our task is to read and write registers. And next step, I'm going to show how we can do that using SPI interface. And for that, let's look at this block diagram. So we have chip select line, okay, as you see. So we have this transition from high to low state, meaning that it will activate the sensor. Then we can send the address of the register, okay, and this we have a write bit. I will explain it later, so right now you can just ignore this. So we send the address of the register and we immediately send data. So this data will be stored in a register that we specified. So for example, if we send 0x57 and 0x32, it means that the value of register with this address, so this is address 57, so the value of this register will be 0x34, and this x is it means it's a hexadecimal number. I hope you are familiar with that notion. And the read operation works in a similar fashion. First we have we again need to send the address of the register that we want to read, but in addition, when we read, we have to set the most significant bit indicating read operation. Okay, then we just send this dump data 0xff, and during that time we will receive data. So this data is the value of the register 0x57. So this is the address of the register. So this data is the register, is the value of the register which has this address. So this is how the SPI interface operates. And again, since we will use the HAL API, you don't need to worry about the details, because the HAL API, the libraries will hold everything, will handle everything. In addition, we can do multiple byte read. So it means that instead of getting data only from a single register, we can get data from series of registers. To do that, we will just keep sending this dump data 0xff. So imagine that we send these 4 bytes. So first we send the address, but also we have to send the most significant bit indicating read operation. Then we have this 3 dump data, and what we get is 3 bytes, which is the values of registers 57, 58, and 59. So it starts from this register, then it will just automatically increment. So we have 57, then we have 58, then we have 59. And the multiple byte write operation works in a similar fashion. So imagine that we send these 4 bytes, 57 and the 3 bytes. So the value of register 57 will be 0x03. So this byte. Then we have 0x58, the next register. Its value will be this byte. Then we have this byte. So this is how we can do multiple byte write and read operations. And finally, I have to explain these two parameters. It might look a bit complicated, but it is actually pretty simple. And during the configuration of the SPI interface, we have to specify that. So these two parameters is clock polarity and clock phase. So when clock polarity is 0, the idle state of the clock line is low. So when we don't have any data transaction, in idle state we have low state in the clock line. The second clock phase, which defines the sampling of the data. So when this clock phase is 0, the data will be sampled on the leading clock edge. Okay, so it will get the bit in this time instance, at this time instance. And when clock phase is equal to 1, the data will be sampled on the second clock edge. So this is kind of details of the SPI interface. If you don't understand it fully, don't worry, because usually inside of the datasheet we have this information, and based on that we will configure the SPI interface. Similarly, when the clock line clock polarity is 1, the idle state of the clock line is high, and we have here leading clock edge and the second clock edge. So this is how the SPI interface operates. Next, we will configure SPI interface using QBMix, a graphical tool. So see you in the next video.